Howdy folks. In our first video this week, we got a look at general acid-base behavior, the idea of giving off an H plus and putting it onto water, or taking on an H plus from water, or for that matter, trading them amongst one another. What we're going to see here is one particular biomolecule that does a little of each, because there are very specific functional groups that are capable of doing this. Not everything can give away an H plus. What you see in front of you here is threonine, which is an amino acid, one of the 20 that we generally make our proteins out of. And this one particularly is an essential amino acids because our bodies can't generate this for ourselves. So we have to consume it in our diet in order to have it available to put into our protein structures. Now, what you'll see present here in this structure, actually I'll have you take a moment and think over which functional groups do you see. Give them names. Okay, if we start on the right side of the molecule, what we will see over here is a carboxylic acid. And remember, that's a carboxylic acid because we, again, have the carbonyl group with an OH attached. Remember, this is not a ketone unless there are carbons on either side. And here we got an O on that right side, so it can't be that. Over to the bottom here, over to the left of it, we have an amine. Notice this N is not directly bound to the carbonyl, so that whole thing is not an amide. That little spacer is enough to turn this just simply into a primary amine bound to one carbon. Do take note that these two groups are what provide the name for this kind of molecule. It is an amino acid, composed of an amine group and an acid group. Now, when these become part of proteins, usually what gives them their individual character is that they each have something different on this end of the alpha carbon, as it's called right here, referred to as alpha because it's the first one after the carboxylic acid. You might remember the one all the way at the end is referred to as omega, back when we were doing unsaturated fats. Now, this particular side chain has got an OH group, and I hope that you rightfully referred to that as an alcohol. Notice, again, just like the amine, not directly bound to the carbonyl. It would have to be for that to be a carboxylic acid. Instead, this is an alcohol. Now, these two functional groups on the right and bottom are the ones that are capable of doing acid-base behavior. We'll talk a little bit about alcohols later. An organic chemist would tell you that an alcohol is a very, very weak acid. However, if you're in water, we're going to see later, for all intents and purposes, it is not an acid or a base. Even though it has an H on an O, just like the carboxylic acid does, even though you see an OH, so you might think base, even with all of that, it's not going to actually detach anything. That's going to stay in place. And I'll show you how we know that mathematically in a little while. Now, these two groups, as I said, are your primary acid and base in organic chemistry. Carboxylic acid, right there in the name, amine, pretty decent base. We even saw that a little while ago when talking about Vicodin, that you could put an H plus onto an amine. And so what we're going to see here is that threonine is capable of acting as both an acid and a base, depending on which functional group gets involved in the party. So we'll take a look here first at threonine acting as an acid, and I'll ask you to pause the video and think over, if threonine is the acid, what is it doing, which functional group can be involved in it, and where does it either put something or take something from in order to do this? Take a moment, pause the video, come on back, and we'll review it together. Okay, now that you're back, your acidic group, as we said before, is the carboxylic acid group right here. And what that means is that if it's an acidic group, then this H plus, note, not just H, but H plus, is capable of detaching and being put onto something else. Well, the only thing over here that's interested in an H plus is the water molecule. And so if this takes place, this is going to now have one more hydrogen and a positive charge, so it will be H3O plus. And continuing the general theme of organic chemistry reactions, I'm not going to change anything else about the threonine. I'm going to rewrite everything else that's present here. So the side chain, unchanged. The stereochemistry, unchanged. Notice that you're looking at a pair of chiral centers there, which is why we have to actually include wedge dash notation. When I get over here, this is where the H has been removed, and as a result, what I now have is a negative charge on the ion. And so this would now be what I get after threonine acts as a base. I don't think it's referred to as threononium, but I kind of like saying it, so maybe. At any rate, we now have that. If I want to go the other direction and have it act as a base, I want you to again consider what functional group would get involved. How would this manifest itself? If threonine is being a base, is it picking up a proton or giving off a proton? Regardless, what is either catching or donating the proton that is being exchanged? Pause the video, take a moment, draw it out, and let's see if you're right. Okay, welcome back again. This time around, if the threonine is the base, then water is going to have to be the acid. And so this time around, water is going to lose one of its H pluses, and that's going to go to the amine, because again, the amine is our chief organic base, whereas the carboxylic acid is our chief organic acid. So again, if this happens, if the H plus is traveling, that means the water still has the O and the H, and it now has a net negative charge because it only lost the nucleus of the hydrogen. It didn't lose its electrons. That nucleus is now stuck here. It's actually made a bond with the lone pair on the nitrogen. And again, nothing else changes. I leave the OH alone. Oops. I leave the carboxylic acid alone. We ignore the little thing I'm scratching out right there because I didn't mean to do that. But then over here, what I've got is NH3 with a positive charge. And so I've now got a cation here. In fact, actually, come to think of it, this would be the threononium. That would be 3 and an 8, maybe? Just kind of trying to go by naming conventions. Not convinced that either of those are quite correct, but I'm going to go look them up after I'm done the video. At any rate, what we've now done is created for this particular molecule its conjugate acid and its conjugate base. So take a moment and pause the video and identify those. Which of these is the conjugate acid of threonine? Which of these is the base? Hoping that what you came up with is that when threonine acted as an acid and lost an H+, what I generated is something that would actually be thirsting for an H+, so that this must be the conjugate acid of threonine. And of course, by process of elimination, that is going to leave this to be, I meant to say base. Dadgummit. Hopefully you're screaming at the video right now and saying, why did he do that? Yeah, I meant to write base. Sometimes writing and talking at the same time doesn't work so well. Sorry, conjugate base right here, because this is the thing that has now picked up NH+ and would be okay probably losing it. In fact, if that double arrow is any indication, it'll definitely do a bit of that. And so I'm sorry, this would be the conjugate acid of threonine. Terribly sorry for the error. Just again, recapping so that it doesn't bother you here. We took the carboxylic acid and turned it into a carboxylate. We stripped it of its H+, which means it's now something that would happily pick up a new H+. That sounds like a thing a base would do. By contrast here, we allowed the threonine to pick up an H+ from water. That left behind hydroxide, and this cation, that thing's got one extra H over here. We know it can go in reverse, and when it does, and it donates that H+, it will be definitely acting an awful lot like an acid.